So let's start. And we all know that today using other people's software is probably usually a basis for creating your own product. The way to go about that is firstly to implement somebody's libraries. And another point is whether a developer wants their software to become part of some larger systems that already exist. They use frameworks for that. What's the difference between using a framework and a library, as in this case? 2 points. Point one, using a framework means architectural limitations for your software. You'll have to write to your software. But when using libraries, your code is the main thing. So you define where certain functions can be used, where certain data sets will be loaded, and so on. So when you call your library, the framework will be calling your code itself, defining where and when your code will be used. Today we're going to talk about one of the most popular frameworks for industrial devices, the so-called software execution environment, CODESYS Runtime. This is our agenda for the next 30 minutes. So we'll talk about the object of our investigation, about the protocol. We'll discuss vulnerabilities and make some conclusions. So what is a CODESYS Runtime? As I've already said, CODESYS Runtime is a framework to create in your device of an execution environment. That's called runtime. What does it mean? It means that your industrial device does not need to be a PLC. It could be a CNC, for instance. Here we see small single-board computers, Russian, German, lots of vendors use this framework to create the devices that are used both in automotives, in windmills, and everywhere. Today, more than 350 devices have already adapted this framework for their industry devices. Here, I'd like to focus on 3 points. 2 years ago, or better say 4 years ago, the number of these devices was twice as low. So today, they are 350. Only 15 adaptations of the framework were made by the CODESYS group developers. All the remaining 330 cases were developed either by their customers or by third parties. And this is the information we took from their official website. We know that in Russia there are at least 6 more companies who use CODESYS Runtime as their foundation for the software, but they're not part of these lists. So this list is not complete. The list should be much more numerous than shown here. So for any runtime, there should be a software development environment. In this case, it's CODESYS development system. In the context of our presentation, it means that CODESYS development system is a customized environment, and based on it, other companies have created their own development environments that carry different names. So what is CODESYS Runtime? It uses component-based architecture. So basically, it's a set of a huge number of components that can go up to 100 or even more. But one way or the other, it's like a Lego set consisting of these components. There are several component groups, so-called system components, communication components, application components, core components, and there's one important component there called Component Manager. What does Component Manager do? It's basically some init process in the Linux system. So everything starts with it and everything ends with it. So how does it work with all other components? The components have a set of certain interfaces, of which we're going to consider only 3. Export, import, the hook function, and that's it. For you to understand what it's all about, let's take this Lego part. So on the top, these little cylinders are some export elements. They are called spikes. And a part also has import features that are called pipes. So the import element takes an export element, and together they comprise a part. An export functions is just a function that can be used by other components. The input function uses these functions in the overall database of exported function. The hook function is the payload of the component as such. The hook function is called by the component manager, and the component manager, every time as this function is called, indicates which events is now happening in the system. For instance, it tells the component, initialize yourself, or abort your work, or start connecting with some other interface, allocate memory, free up memory. And every time it calls this function. So there are 20 events, and every time they are mirrored. So the next question, what does it mean to adapt the CODESYS runtime for your device? It means that the developer who's going to use this CODESYS runtime for their device need to implement system components. There are 20 system components. After they've implemented this code of the system components, the system components automatically export functions. Then the rest of the components import them, and this way it builds a certain foundation, or we call it pad, for other components, through which all other components keep working steadily within the system. Now, as I've already said, the developers of CODESYS group implemented more than 15 of showcase adaptation of their products. There are adaptations for implementations for Raspberry, and there's also soft PLC for Linux. We've taken those implementations and took a look at what they are about. The important thing is that all the executable files are packed, but as they are unpacked, so I mean the software code is packed. We can't insert it into a debugger, for instance, or disassemble it to take a look what's happening in this program. We need to unpack it first. The unpacking process is happening in an unsafe way. So after the unpacking, and as these files are executed, there are some vulnerabilities there that can be exploited. That an exploitation of one vulnerability will happen in a much simpler way than it could have been. In addition to the very fact that the compilation of file happens without secure options. The next important process. The executable file is run as a single process. CODESYS runtime consists of like 6 different services, about 10 threads, and all of them are run as a single process, which means that if, this CODESYS runtime is working, if something drops, then the entire executable goes down. And also, it has a lot of components to improve the protection. There are encryption components, application signature, but they're all disabled to start with. So this is the way they've organized their work, insecure by default. We, in the first place, of course, also studied the proprietary protocol that they implemented. In order to move further, you need just to understand what this protocol is all about. In the first place, this protocol is not restricted to SSO communication over the internet. This protocol has already been implemented for such communications, USB, CAN bus, or serial ports. Then, it's not just a protocol, it's a protocol stack that contains 4 different levels. The so-called block driver, datagram, channel level, and services. The protocol as such is based on the ISO CI models, and it can run both in sync and async mode depending on the current layer in this protocol. In previous conferences, such as S4 in Miami or PhD, we just explained what this packet, how this packet looks like and how it works. So this is the packet that contains the certification data, login and password. Take a look at this humongous number of fields contained in this packet. It's clear that every one of these fields serves some engineering function. But apart from that, some fields refer to other fields. Third kind of fields are a whole binary structure rather than one field. For instance, holy packet info, basically containing several fields in one. Unfortunately, today we're very limited in time, so I'll share the top 6 fun facts about this protocol. The first one is, as I already said, the CODESYS protocol is based on the ICO-OCI model, but CODESYS runtime uses the capabilities of the operating system and the drivers. If this CODESYS runtime has been launched together with the operating system, because you can actually adapt the code runtime without operating system. So if your packet has been sent over a TCP connection, not only will it contain the CODESYS PDU stack, but it also contains this list of protocols. So you'll have 2 ICO-OCI models in one package. Funny, isn't it? So every packet is going to be processed by more than 10 components at the same time. As I've said, there are 4 different levels. Very quickly about this level. Block driver is like a level which components are needed to implement communication over some physical interface. The second level, so the datagram layer, it's required to understand what this packet wants from it. For instance, it can want to this packet can want to know what this device is all about. And second, it's needed to understand the parameter of the packet, how fast it can be processed, at which moment in time it should be processed. So the overall task of these levels passes down to the lowest level in such situations later. A higher level, a channel layer, needs to get data synchronized to understand if the packet has been lost, if all the data has been passed, has any data remained, and in addition to that, a communication channel needs to be established between them. After all fields have been processed and it's become clear that this packet is required to execute some operation in the services layer, we complete the processing of this packet. But there are certain things that need to happen. First, the driver block is an ingress and egress point for packets. So that's why these drivers very egoistically allow adding some other additional fields in addition to the huge number that we already had. For instance, we have this packet that's been sent over TCP. The driver added its own magic line and also added a very funny size. So usually this size normally it refers to the remainder, the size of the remainder data, but it shows the size of the remaining data, the current size, which sounds a bit silly. In the UDP communication, all these fields will be absent. The next point. The CODESYS PDU packet must contain addresses of the sender and receiver. The sender is basically the address that needs to process the packet. The receiver is the address that needs to receive the result of this processing. There are 2 types of addressing in CODESYS PDU, direct and relative. Direct addressing is when you use these 4 bytes of the address line, a typical address line, a stamp, and 2 port bytes. A question: why do we need these fields here if they are part of the IP protocol? But nevertheless, it's them exactly that are going to be used. There's also an offset address or a relative address that's used in UDP connections. So instead of the 4 bytes of the address as such, you only have one last byte. And in the place of 2 bytes, you have the last byte of this address. Instead of 1 byte, port byte, you only have one value of the port index, which means an index with 1740 plus index. So then you'll be able to restore the end port. The processing is done like this. You take the packet, you take this sender and receiver addresses, and then this node in its own subsystem adds this address and forwards or responds to this packet. Why this all? They implemented the so-called tree topology in their addressing. So you have some child node, it's the parent node. It can ping another child node, even though they have different physical connections. For instance, here we use a CAN bus, we here Ethernet, and this is USB. So this node will contain the address of the parent node, which is 122 here, and if it builds a packet saying that we need the address of this node, it will show the address of its parent node. It's forwards this packet to its own parent node. Then it will read the next parent node address, and in this way, certain information network will be built involving all these nodes. It's a very cool solution. Another fun fact is that at the final service level, 10, 15 to 20 components are used. The funny thing is that in order to check in a component at the process level, you need to export a function from another component. So at one time, this processor can only be registered by a component only once. So one component may not have more than one such processor and the handler. And finally, it's about encryption enabled between PLC and IDE environments. For this, you take and run the development environment, indicate that a certificate needs to be issued to the PLC, then they exchange certificates, and then instead of a gray line, you're starting to get this red line between them, which means an encrypted connection. I've already shown this package. Actually, it means that you get only part of this data encrypted, starting from a certain level, that is, from the services level. All the other data generated following this protocol, the block layer, datagram layer, are not going to be encrypted. So the attacker can always read them if they have mitten. And the question, do they have mitten? For us to identify the vulnerability, we use one simple thing. If this protocol has been based on the OSI protocol, can it have the same vulnerabilities that the model contains? A spoiler. There's a classic attack called address spoofing. It's used where attackers want to get addresses of the maximum number of participants in the network after the attack. For this, they include a special packet saying that it's not them who've sent this packet, but it was sent from another node. The victim gets this and sends the result of the processing of this component to the node indicating this field. So this way, the attacker will stay more or less covert. In our case, we've seen CODESYS PDU shows how to use these two different addresses, and we can organize a classic IP spoofing attack. But the datagram level, apart from address processing, it's also used for the routing of this process. As I've said, we have this tree-like architecture, so the attacker can manipulate one other additional address to the main one, making this attack more difficult for analysis, obfuscating this attack for other people. That's not everything. In the IP spoofing attack, there's a typical problem where the attacker doesn't get the result of the address processing. A question: how to get this result, staying more or less invisible? The block driver, the UDP block driver, apart from running on UDP protocol, also listens to broadcast management and may also send the packet processing result to our broadcast address. So this way, the attacker can indicate that the packet processing result should not be sent to a specific address, but to this broadcast address, and so that the results of the processing could be shared. But there's another cool thing about it. The node as such doesn't care who comes to it directly, because it doesn't look at the IP protocol. It looks at the data received over the CODESYS PDU protocol. So therefore, an attacker can use this to communicate to the victim's node that the broadcast address is being used to exchange with them. So it thinks that the broadcast node is used, whereas in real life it's just a regular node. So in this case, the attacker can use several addresses to organize the attack. From the previous vulnerability, we can see that there's an opportunity to get inserted into the communication link. So the attacker can send some packet to the address of some node, just like here. It sends the packet to one node. The node believes that it needs to forward this packet to the victim node just because it trusts all the incoming data. And this way, the attacker gains an opportunity of inserting itself to the existing link, even though it has to handle the certificate and ID issue. But the communication ID can be received in the very simple way. Every time you connect it to some nodes with CODESYS runtime, you request the channel ID, and it'll be implemented in different numbers of such communication links. So learning this ID is quite simple. We've also found a vulnerability to get the session ID after authentication, because it is generated in a pseudo-random way. A vulnerability called MITM. You know, there's such a thing as RP protocol, and we found something similar to it in this CODESYS runtime. And it works like this. In order to build knowledge about the parent node, there are two ways. Way one, to do it statically, to set this data using the configuration file. And the second way is to do it dynamically, so that the attacker can send a specifically built packet that will say, look, I'm your father. And after that, the PLC will think that it's got a new parent node. And now, every time when somebody requests or comes to this PLC with some message, it will redirect traffic to the new parent node. So this way, we are going to have MITM implemented. And here you have to remember once more that all the data in this packet will be encrypted, and if they're not encrypted, so what can be done? Yeah, there's another important thing here. It's important that the UDP block driver listens to a broadcast response. So the attacker can send a request to the broadcast address, request, and this request will be received by all the nodes at the same time. Because of that, all nodes set as a parent node will get the attacker address, and all the traffic will start getting channeled through this address. So the question, what can we do about that? We found a vulnerability that exists in the password encryption protocol. So what's it about? Here, so the green here is our encrypted password. How is it built? Firstly, you have some fixed key that you do XOR, byte by byte XOR. And because XOR is a symmetric operation, you can take this fixed operation. We can use this key to get an encryption password and some symbols. The question, why not all symbols have been decrypted? A very simple answer. Here, we're also sending a one-time value, 4 bytes. So actually only 1 byte out of these 4 will be used. Why? Because so this is need to make password decryption more difficult. And the last vulnerability that we identified was related to the vulnerability in the compiled application code. We had known that a system compiles the application native machine code that's been written in IDE. So we took some simple program where we indicated 2 rarely encountered numbers, dead beef and beef. So one we mentioned in the body of the program and the other in the header. After that, we started looking for dimensions of these 2 variables in the traffic, and we found them exactly 2 times for each of them. So here we found a dimension where we were showing in the body of the program, and here we found the reference that we had in the header. So what did we do next? So we took the data from this traffic, ran static analysis, and found quite a predictable thing. We found that it's machine code. It's an ARM code. It's ARM code showed here because we were building a program for Raspberry Pi. So what is happening here in this code? So here we assign a value, here we assign an address, and then we write an address, a value for this address. It all looks on declaring a variable in the header of the program as such. And the second mention went like this. So we took the same address, we took the value from this address, and then we wrote the beef value and added them one with the other, and then wrote the resulting address value in this address. So we got a sum of the previous value with a fixed value. So we've read this value and added the other thing to it and wrote it again. So what's it leading to? We identified 2 places where, instead of the code generated by the engineering environment, to write our own code. So it's important to mention here that apart from the service that they've implemented in Linux, they're already run from root. So you don't need to deal with privileges. For the server, the thing has been launched with the system attributes, so there's no point. So, conclusion, what did you want to show in this work? One way or the other, all the vulnerabilities that we've found could have been found had the developers of this protocol opened the protocol specification. 350 devices were built by 40 vendors. 40 vendors were developing for this framework in different devices. Had they had a specification for this protocol, I'm sure at least somebody should have come back to CODESYS group and asked them, why is it running this way? In certain places, you have a huge number of vulnerabilities. But nevertheless, it didn't happen because it was closed. So what follows from this is that security for security is not a strategy. It's a method to cover up. And here I can say that always people will be found who will research your product, your protocol, and find the vulnerabilities. Oh, by the way, it's an Easter egg. If you run Raspberry Pi with these arguments, it'll say goodbye to you showing a cow. Whereas I'm saying thank you to you in Russian, and I'm sorry for taking a bit more of your time.